Good evening. Um, Picture this. Picture you place a flashlight on a distant mountaintop, maybe 3 miles away, and you're observing that flashlight, and your job is to observe that flashlight and tell when a moth passes in front of that flashlight. Now, picture this. Picture the moth flying in front of that, and you want to tell me what color that moth's wings are. That transitions into what I would like to speak to today about the evolution of exoplanetary characterization. That's kind of what we deal with when we're looking at characterizing these exoplanets. We're looking at the atmospheres of these, and it's very similar to trying to figure out what color that moth's wings are from just the light coming from that flashlight, and of course, that light being from a star. Um, we have a transition. Our first optical pioneer, the Hubble Space Telescope, and it transitioned to the James Webb Space Telescope. Hubble had an incredible run. There was an incredible legacy. It had a 2.4 meter mirror, and it had coverage from UV to near infrared. And James Webb Space Telescope, it represents a huge revolution. It has a 6.5 meter mirror and a larger spectral range, which reaches deep into the mid-infrared. You can imagine Hubble is looking through a tiny keyhole in the spectrum, whereas James Webb Space Telescope is looking through a large window. As you can see from the graphic here, the spectral range for Hubble was 0.1 to 1.7 micrometers. And with James Webb Space Telescope, it's 0.6 to 28.5 micrometers. You can see the large difference between the two. So the overarching scientific goal is to move from simply detecting or identifying that a planet exists via the light curves, like I mentioned before with the moth traveling in front of the flashlight. We were able to measure the dip in the light from that star and say, hey, there is a planet there. And we are going to true characterization where we can map the physical and chemical properties of the atmospheres of these exoplanets, which are millions and millions of miles away. Initially, this was hampered by guesswork due to the instrumentation or the instrument limitations, but we are now finally resolving these. So the primary method or the tool is transmission spectroscopy. During a transit, the host star acts as a backlight, and as light filters through the translucent annulus of the exoplanet's atmosphere, more specifically, if the solid body of the planet blocks out the light, we can read the light that's coming through the atmosphere, and it will emit very specific molecules absorb distinct wavelengths. By capturing this with a spectrograph, we can decode the molecular fingerprint of that distant world, so we can actually figure out what that atmosphere is made of by looking at that, through spectroscopy. So physics, it kind of dictates our success here through the scale height, which is known as A. So that's the scale height, or I'm sorry, not known as A, as H. The H is equal to the Boltzmann constant times the atmospheric temperature over the mean molecular weight, which is the composition of the atmosphere, times the surface gravity. So if you have a high T, like a high atmospheric temperature, and a low molecular weight, and you would have a large scale height. And conversely, with a low T, a high molecular weight, you would have a high scale height. So in the equation here, H is proportional to temperature and inversely proportional to the molecular weight and gravity. So, put simply, hot gas giants with low density atmospheres create a puffy target, like something, it gives us more target to look through. Um, and it's much easier for us to detect gas giants than rocky planets who have an atmosphere that's compressed and really tight around that rocky core. So Hubble's narrow spectral window led to model degeneracy because we were looking through a narrow keyhole, a real small band. Um, there were different atmospheric conditions like clear skies versus high opaque clouds. They could produce the same signal. So we were really just kind of guessing. So um, we would feed that into a computer, and that computer would give a best guess as to what that atmosphere was made of, even though we really had no clue. So James Webb Space Telescope solves this by expanding our coverage into the mid-infrared by accessing these longer wavelengths. We aren't just seeing fuzz; we're capturing distinct vibrational, rotational, molecular signatures. This allows us to resolve those degeneracies that limited Hubble and provides a continuous high-resolution view of the atmosphere. So WASP 39b, that's our easy mode. Um, it's basically a hot bloated Saturn. It's a Saturn mass gas giant. It provides a massive signal. JWST's near spec instrument allows us to perform simultaneous and robust detections of water, carbon dioxide, carbon monoxide, sodium, and giving us a clear picture of its composition. So that's really an easy target. It's one of those. It's one of the gas giants that we have a clearer view of its actual atmosphere. So one of the most exciting findings was the discovery of sulfur dioxide. We saw a prominent absorption peak that static models did not predict. This provided concrete proof of active photochemistry, where UV light from the host star breaks down molecules to create new ones, proving these atmospheres are dynamic, living chemical systems. So now we face the hard target, rocky exoplanets, the ones with the tighter clinging atmospheres to that planet. So TRAPPIST 1e is an example of this. There's high surface gravity and cooler temperatures that compress the atmosphere, making the scale height very small. The current challenge is the 5 scale height barrier, where we need extreme precision to extract these tiny signals from the stellar noise. So, we're looking at a very thin sliver of that annulus around the planet, and you have this really bright star that's putting off a lot of light, and we're trying to extract just a very tiny bit of signal from that. So the leap in our capabilities is best seen in our confidence levels. For water vapor, Hubble achieved a detection confidence of about 3.2 sigma. With identical simulations, JWST's nearest instrument pushes that confidence to over 8.5 sigma. We're no longer working at the edge of detection. We are working in the realm of high precision science. So we're solving old problems and uncovering new ones. So there is a cost to the high sensitivity. JWST has effectively resolved the wide wavelength observational guesswork that limited previous missions. Its pristine data quality has unmasked deeper, more intricate physical challenges, stellar contamination. Uncompromised data means uncompromised views of the host star itself. Signals from star spots can easily warp or fake molecular spots in an exoplanet spectrum. So, if there's a star spot, we could mistakenly think that that is another chemical or some other portion of that atmosphere. So there's subtle uncorrected electromagnetic signals or cold spots on the stellar surface that can easily warp transit depths, faking or obscuring critical molecular absorption spikes in the resulting exoplanet spectrum. Like I was saying, if there's one there, we could confuse it with something else. So there is a 1D model limitation. Historical inverse atmospheric retrieval models rely on a simplified one-dimensional average calculation of the atmospheric column. The intricate 3D realities, real exoplanetary atmospheres exhibit highly complex three-dimensional dynamics, including localized cloud decks, morning to evening terminator variations, and severe horizontal temperature gradients. So we have to employ these different computer models to help avoid systematic bias with overabundance of estimations. So looking ahead, we're moving from the JWST era of discovery to a future of direct characterization. The LIFE mission using a nulling interferometer will allow us to suppress the light of the host star directly, bypassing the lucky alignment requirements of transits to sample rocky atmospheres. So, in conclusion, JWST didn't make exoplanet physics easy. Instead, it moved the goalposts. So, we've shifted our inquiry from being limited by our instruments to now grappling with the complex three-dimensional physical nature of these worlds. We have graduated from statistical guesswork to an era of planetary science.